This video is part of a free training package we've created to help you with your CPD. You can either watch the video here or you can click the link in the description to access the video, answer some multiple choice questions and receive a free CPD UK accredited certificate. In this free training package we'll be looking at the subject of three-phase electrical systems and we're going to consider the following subjects. What is three-phase electricity? Why do we use it and how do we use it? What are the relationships between voltages and currents in a three-phase system? What are the colours used for three-phase supplies? And we're going to illustrate these points using some of these products from Luden Palazzoli. So let's get into it. What is three-phase electricity? To really understand what three-phase electricity is, we need to understand how it's generated. Electricity can be made in one of three different ways: chemical, thermal and magnetic. To generate large amounts of electricity, we tend to use the magnetic method. It's a fundamental fact of physics that if you move a conductor through a magnetic field, it will generate electricity inside the conductor. If we take the conductor and wrap it into a loop and spin this loop inside a magnetic field, it will generate electricity inside the conductor, which can then be extracted. Depending on how we extract this electricity, we get either DC using what's called a commutator or AC by using slip rings. To make a practical generator that will generate enough electricity to be useful, we don't just have a single loop of conductor, but rather we wrap the conductor round many times, turning it into a coil. This effectively increases the length of the conductor cutting through the magnetic field, which increases the EMF from the generator. Now, to generate three-phase electricity, we use three coils of conductor. We've gone back to single loops here to keep the principle clear. And we offset these loops of conductor from each other by 120 degrees. As these three conductors are spun inside the magnetic field, we get three AC waveforms that are exactly the same as each other, but rising and falling at different points. They are offset by 120 degrees, as you can see from this representation here. Now, if we scale this up to the size of a power station and try to extract large volumes of electricity from inside here, it very quickly becomes difficult, expensive and impractical to construct and maintain. So in reality, we swap things over. Instead of spinning the coil of conductor inside the magnetic field, we put the coils around the outside of the machine and spin the magnet inside. The magnetic field is then spun around inside the generator. And because creating very large, very powerful permanent magnets is again difficult, expensive and impractical, we use a coil of copper and pass DC current through it instead. This creates a powerful electromagnet instead, which gives us further control over how strong the magnetic field inside there is. Now, at this point, it may seem a bit strange that we're using electricity in the electromagnetic coil to produce electricity out of the machine, and you may be wondering why we don't just use the electricity in the coil and cut out the middleman. It's a reasonable question, but bear in mind the electricity into the coil is just generating a magnetic field for us to turn around and drive the electricity out of the generator. It's the turning power that we apply to the rotating magnetic field that generates the electricity. And if you've ever tried it by hand, you get a really good idea of how much energy it takes to generate even relatively small amounts of power. This turning power has until recent times been powered mostly by steam turbines powered by burning stuff like gas, coal and oil, but of course we're now trying to move away from these to more renewable sources like wind, tidal and hydro. But back to our generator. The coils on the outside are again offset by 120 degrees and in reality will consist of several coils spread around the outside of the generator to maximise efficiency. But again, keeping it simple helps us to understand the principles involved. One end of each coil is connected to the ends of the other coils in one of two ways to give us either a star or a delta connection depending on the type of generator it is, and the other ends of the coils are connected to the outside world, giving us our three-phase supply. So that's how a three-phase electricity supply is created, which nicely leads us on to the next question: why do we do all that? Well, first of all, let's answer the question, why do we use AC over DC in our distribution system? Well, for over a century now, we've used a model where we generate large amounts of electricity at big power stations a long way away from where we need it. This makes sense, after all, who'd like a coal-fired power station on their doorstep? So we need to get the electricity from the power station to the point of use. As electricity has to travel further and further from where it's made to where it's used, the voltage gets lower and lower, and if it gets too low, it won't do what we need it to do. One way to get around this is to start with a massive voltage, so it's still at a usable level when it gets to where it's needed. This is, however, enormously inefficient. A better way is to generate at a manageable voltage, then step it up to a much higher value for transmitting long distances, and then stepping it down when it gets to where it's going to be used. In the early years of electricity transmission, doing this to DC was a bit tricky and inefficient, but it was found to be quite straightforward and efficient to do it to AC using relatively simple bits of kit called transformers. So we started using AC because it was an efficient way to transmit electricity long distances while giving us usable, manageable voltages where it gets used. Since then, there's been huge advances with modern electronics that has made stepping DC up and down easier and more efficient, making transmitting DC long distances much more efficient. We even use DC to connect countries together, like the high voltage DC connection between the UK and France. Indeed, with the rise of large-scale solar PV farms that generate DC and the increased efficiency in power electronics, it could be argued we'd be better off going to a DC transmission system rather than converting DC to AC to send long distances and then often converting back to DC for a lot of electronic loads. After all, the other large-scale load most people use electricity for is heating and lighting, which can be done just as happily with DC as AC. Anyway, that's a debate for another time. For now, and for the foreseeable future, we're using AC for transmission as that's what we're set up for. But why three-phase AC? Well, it has a couple of advantages. The first is that three-phase can be used to drive motors. An induction motor can be built incredibly simply with very few parts that wear out and require maintenance. They can also be made relatively compact when compared to equivalent single-phase motors. This makes them cheap to buy and maintain and to operate reliably. For a long time, it was tricky to finely control their speed, which gave the edge to DC motors in certain applications, but the advent of variable frequency drives has ensured the three-phase motor has become the workhorse of industry. Another benefit of a three-phase system is that if the generator or transformer supplying installation is connected in star, it creates an opportunity to connect a neutral conductor. This in turn allows for the connection of both three-phase and single-phase loads to the same supply with two different voltages. We can also connect our loads, which in this example are generally motors, either in star or in delta. This will give the motor different characteristics of torque and power. We can even start a motor in star and then switch to delta to limit the current that flows into the motor on startup. Let's dive into the different voltages and currents that are found in three-phase circuits and the relationships between them. If we've got a three-phase load, we can represent the three parts of the load using resistors. Now at this stage we should point out that if we're representing a motor, we should technically use coils and resistors in series to represent the windings, but then we're going to start straying off into inductive reactance and power factor and all kinds of things that will only confuse matters for this subject. More on that in future content. So we've got our three resistors representing the three-phase load. There are two ways that we can connect these together in a three-phase system. We can either connect them in star or delta. A star connection is usually represented like this, hence the name star, as the loads are fanned out looking much like a star. A delta connection looks like this and takes its name from the name of a letter in the Greek alphabet that looks a bit like a triangle. Now it's important to bear in mind that these diagrams don't show the literal physical layout of the loads. Going back to our motor illustration, you can swap the motor between a star and delta connection by changing the way the connections are made, but the physical structure of the motor doesn't change. We could just as easily show a star and delta connection like this, but it's not quite as clear how the different bits connect together. So what difference do the two types of connection make? Well, in both types of connection, there's two different currents to be aware of and two different types of voltage. These are called line voltage and phase voltage, and line current and phase current. I like to define them in the following ways, as it applies equally to both star and delta connected loads. Line voltage is the voltage between any two of the supply lines. Phase voltage is the voltage measured across the load. In a star connected load, it's tempting to think of this as the voltage between line and neutral, which it most definitely is, but that definition won't work for the delta connected load as there is no neutral connection. Continuing, line current is the current in any of the supply lines and phase current is the current through any one of the loads. Having these definitions clearly in mind will help us to understand the relationships between the values. If we look at the voltages in the star connection to begin with, you probably know from experience that measuring across the load, effectively measuring between line and neutral, gives us 230 volts in a standard UK system. Measuring between any two lines should give us 400 volts. How are these two voltages related? Well, it turns out it's by a special number, which is the square root of 3. If you multiply 230 volts by the square root of 3, or approximately 1.732, you get just over 398 volts, which we round to 400 volts because it's easy to remember. And after all, what's a couple of volts between friends? Looking at the currents in the star connection, you can see that any current flowing through this load has to flow through the line that's connected to it. It has to pass along that conductor to pass through the load. So that means in a star connected load, the line current and the phase current are equal. However, when we move to the delta connected load, things are a little different. First, let's take the voltages. Bearing in mind the definition of phase voltage first of all, this is the voltage across the load and would be measured here. However, if we remember that the line voltage is the voltage between any two lines, you can see that electrically there's absolutely no difference between connecting your voltmeter up here and here. This means that the line voltage and the phase voltage in a delta connected load are equal. However, when we consider the line and phase currents in a delta connection, something interesting happens. Remember that the phase current is the current through the load. So the current here is being drawn down this conductor, but also flowing down this conductor is some of the current being drawn from this load. Now we don't simply add these two currents together because, as we saw from our waveform earlier, they're out of phase with each other. Now it may not surprise you to learn that the relationship between these two currents is once again the square root of 3. The line current will be the phase current multiplied by the square root of 3, or approximately 1.732. All very interesting, but what are the practical benefits behind these relationships? Well, let's do a comparison between a load supplied by a single phase supply and a three-phase supply. Now, we're not suggesting here that you can simply convert and switch between single phase and three-phase supplies for any load. We're just going to compare the numbers for transmitting a given amount of power. So let's take a fairly beefy installation and say it's a 23 kilowatt load. If we do a quick calculation to find out how big the cable to supply this load will be, we need to first of all find out how much current it will draw. Power in a single phase circuit is calculated with the formula P equals I times V. We could volley on an extra multiplier of cos theta on the end there for power factor, but again we'll keep it simple and cover that elsewhere. So to calculate the current drawn by the single phase load, we'd rearrange the formula so that it looks like this. I is equal to P divided by V, or current is equal to power divided by voltage. 23,000 watts divided by 230 volts is 100 amps. How very neat. It's almost like I planned it that way. Now we're skipping over the design process a little bit here. There's some other steps that we should take in between here and here. We're just trying to prove a point about the efficiency of three-phase electricity here. So if we're using an armoured cable to supply this load, BS7671 table 4D4A shows us that if the cable is mounted on cable tray, it would need to be a 25mm cable, as that can carry 128 amps. If we were to supply that same 23 kilowatt load with a three-phase supply, what difference would it make? Well, the relationship between power, voltage and current in a three-phase system is similar to the one for a single-phase system, but with a couple of key differences. It looks like this. P equals I times V times by the square root of 3. You may see this root 3 at the start of the formula, but I've put it here as, depending on what calculator you're using, that root symbol can extend over the multipliers, which will give you an incorrect answer. The question that is hopefully springing to your mind now is, which current and voltage do we use? Well, the answer is the line current and the line voltage, the two biggest values from our three-phase calculations. And this formula is true for both star and delta connected loads. So rearranging to find the current, our formula turns into this. I is equal to P divided by V times root 3. So line current equals the power divided by line voltage times root 3. Popping the numbers in, we get 23,000 watts divided by 400 volts multiplied by root 3. And the line current will be equal to 33.2 amperes, or in other words, a third of the current will flow in each conductor, which makes perfect sense because the power is being transferred between three line conductors, so a third of the current will flow in each. The practical impact of this is that if we look back to table 4D4A of BS7671, you can see we could install a 4mm cable instead of a 25mm cable. It's a pretty close thing, as the cable can carry 35 amps and some of the rating factors may tweak this up to 6mm, but even if it does, a 4-core 6mm cable is going to be so much cheaper to install than a 25mm 2 or 3-core cable. We can debate the merits of separate CPCs versus integrated CPCs versus armouring elsewhere. And not only does this reduce the cost of cabling, it's going to be lighter and the conductors are going to be much easier to bend and manipulate into terminals and connect. So this may raise the question, if three-phase is so good and efficient, why aren't we using it everywhere, especially in domestic properties? Well, the answer is that we kind of are. With increased electrical loading from EVs, heat pumps and other electric heating, some larger domestic properties are starting to either have three-phase supplies from new or having their existing single-phase supplies upgraded. Up until now, it's really been a question of loading. The benefits of three-phase over single-phase are much narrower on smaller loads, and until now most domestic properties can be considered to be pretty light loads compared with large industrial manufacturing units. But the installation of three-phase to domestic properties may well become an increasing trend over the coming years. Watch this space. Moving on from the science behind three-phase systems, let's dive further into BS 76M1 and take a look at some of the regulations relating to it. We're going to have a look at a section we may have a tendency to overlook sometimes. That's section 514, which relates to identification and notices. The direction that outlines why we use the colours we do is found in part in regulation 514.3.1, which reads, except where identification is not required by regulation 514.6, cores of cables shall be identified by 1. Colour as required by regulation 514.4 and or 2. Letters and or numbers as required by regulation 514.5. Now, because we're primarily interested in the colour identifiers of cables, we're going to leap into the regulation quoted in indent 1 there, which is 514.4. We can skip past the intervening regulations as they relate to specific conductors, namely neutral, protective and pen conductors. Regulation 514.4.4 is really simple. It just states that other conductors shall be identified by colour in accordance with table 51. So this is where we find our information on conductor colours, including for three-phase systems. Under the subheading AC power circuit, we find that for line 1 of a three-phase AC circuit, the identifying colour is brown. For line 2, we have black, and for line 3, grey is the identifying colour. If a neutral is required for a three-phase system, then blue is used, the same as it would be in a single-phase circuit. Now, it may be that when you open up an old consumer unit or a piece of trunking, you come across conductors that are completely different colours for a three-phase system. These are most likely to be red, yellow and blue. These conductors are identified under an older system of colour coding that was replaced in 2004. Under this system, L1 was coloured red, L2 was identified by yellow insulation, and L3 was blue, with black standing in for the neutral in a single-phase system and also in a three-phase system if required. Now, as you can imagine, there might be certain circumstances where a measure of danger would come into play with this change. The outstanding example being that when the colour change occurred, blue and black swapped from being a line and neutral respectively to exactly the opposite under the new colours. This could have led to all sorts of problems. So why was it changed, and how were those potential dangers mitigated? Well, it's important to bear in mind that the electrical trade is still in its relative infancy really. People have been constructing buildings using bricks and timber for thousands of years. We've only been wiring them up for just over 100. This means that standards and methods are still settling into place, coupled with the exponential rate that technology is developing at and closer connections to the wider world all means that change is inevitable. There's a tendency in some areas of the electrical community to view the old colours as being the way it should be done because that's the way it was always done, and how dare bureaucrats from other countries mess with our wiring systems in the name of harmonisation. Well, just to temper that a little, it may surprise you to know that if you go back far enough, there were previous iterations of wiring colours. For instance, rather than red, yellow and blue for three-phase, the UK used to use red, white and blue. You may come across this in very old installations predating the 1960s. I've seen it once in an old supply to an old manufacturing building in Leicester city centre that was being renovated. But even before this, we were using all kinds of colour combos, red, white and green, red, yellow and green, even a blue neutral for a while back in the 1920s. So it was hardly electrical heresy to change the conductor colours in 2004. Another thing I had no idea about until I started researching this subject is that the colour change was not forced on the UK from continental Europe, but rather it was kind of the other way round. The UK requested that installation wiring across Europe be harmonised as a kind of bargaining chip when they harmonised colours in flexes. And not only did the UK push for harmonisation in fixed wiring, they also suggested the colours that we now use for three-phase, as most European countries were using a mishmash of brown and black that were often interchangeable with each other. Simply using the red, yellow and blue that had been used in the UK for a long time wasn't an option for harmonisation, as Germany and Austria had been using red for a protective conductor and yellow was being used for the same purpose in Italy. You can readily imagine the dangers for swapping those colours to line conductors in those countries. Initially, the UK proposed using brown, black and white, but cable manufacturers asked for grey to be the third colour as it was easier to manufacture. This was all agreed and harmonisation took place. All in all, this process took somewhere around 40 years to complete, ending in 2004 with the changed, harmonised colours being adopted in the UK. Hardly a rushed and ill thought out process, to be fair, and one that was largely prompted and promoted by the United Kingdom. It seems that the so-called new colours are now so embedded and ubiquitous that the risk of harm from installations featuring old colours that are being modified or with mixed colours has been satisfactorily managed to the point where we should probably stop calling them new colours. It has been nigh on 20 years since the changeover, to be fair. This is evidenced by the fact that if you turn to Regulation 514.14 in the Second Amendment to the 18th edition, you can see that there is a regulation there that's been removed. And this is something that kind of passed me by when the Second Amendment landed, so what was there? Well, if we turn to the 2018 edition before any amendments were made, you'll find the removed regulation. And it states, if wiring additions or alterations are made to an installation such that some of the wiring complies with Regulation 514.4, but there is also wiring to a previous version of these regulations, a warning notice shall be affixed at or near the appropriate distribution board with the following wording. Caution. This installation has wiring colours to 2 versions of BS 7671. Great care should be taken before undertaking extension, alteration or repair that all conductors are correctly identified. So that's a very sensible precaution to take, but it's no longer a requirement under the Second Amendment. In addition to this, Appendix 7 of the 18th edition contains some further information on harmonised cable colours and some additional precautions you could take to help you further reduce the risks presented with mixed versions of cable colours, including, in paragraph 2, the suggestion that, where an addition or an alteration is made to a 2 or 3 phase installation wired in the old core colours with cable to the new core colours, unambiguous identification is required at the interface. Cores should be marked as follows. Neutral conductors. Old and new conductors marked with an N. Line conductors. Old and new conductors marked with L1, L2, L3 as appropriate. So a sensible precaution to remove any doubt as to what purpose the conductors are serving. This is especially useful to overcome the challenge mentioned earlier with the blue line conductor becoming black and vice versa for the neutral. However, under the Second Amendment, this whole Appendix 7 has also been removed. So why are these eminently sensible precautionary methods no longer required? Well, it's probably to do with what we mentioned a moment ago. It's been nearly 20 years since the cable colours changed, so we're getting to the point where a lot of the wiring installed prior to that year might need replacing. That's not to say that it has to be replaced after a certain amount of time. If installed correctly, electrical wiring is hardy stuff that can keep on doing its job for decades. Also, during that period of time since the change, there's been a huge amount of new installations built and existing installations rewired with the new colours. On top of that, the electrical industry has had plenty of time to get used to the idea that they might come across old colours or a mix of the two on installations they might be modifying. All this means the risk presented by mixes of the two are getting gradually reduced over time. Of course, it may be that you wish to keep following the guidance from previous versions of the regs and leave the warning labels, etc. However, you no longer need to do so in order to remain compliant. So there we go. We've looked at what three-phase electricity is, why and how we use it, what the relationships between three-phase currents and voltages are, and we've had a brief historical tour of the three-phase colours. To complete this CPD module and receive your certificate, please continue on to answer the multiple choice questions by either clicking next if you're on our website, or click the link in the description if you're watching on YouTube. All that remains in this video is to say thank you very much for watching.